Hello, welcome to my video on data structures. In this video, we will discuss the separate chaining approach. In the previous video, we discussed the basic idea for hash table. One problem remaining is how to handle hash collisions. That is, how to handle the case when different keys correspond to the same hash value and compete for the same position in the hash table. The idea of separate chaining is to simply extend the hash table from one-dimensional to two-dimensional. When collision happens, we will simply append the new record to the existing records. Recall the example discussed in the previous video. The records for Alex and Tom lead to a hash collision, and both compete for the fourth position in the hash table. The idea of separate chaining is, instead of overwriting Alex's record, we will simply append Tom's record to the Alex record. The colliding records thus form a chain, and that is why this approach is called the separate chaining. Now, let's briefly discuss the implementation of separate chaining. As discussed before, hash table implementing separate chaining can be viewed as a two-dimensional table. The first dimension corresponds to the primary table, which is a vector that contains a set of linked list addresses. A record's hash value will be used to determine its position in the primary table. An entry in the primary table is called a hash bucket, or simply a bucket. The second dimension corresponds to linked list, where each stores a set of colliding records. When inserting a record, we first calculate the hash value using its key. We then use the hash value to locate the position in the primary table. Then, we append the record to the linked list at the corresponding location. We can append the record by calling the pushback function of linked list. When searching or deleting a record, we also calculate its hash value first. Similarly, we then use the hash value to locate its hash bucket. Then, we compare the search key with all records in the linked list. And we claim the record is found or delete the record if the keys match. With separate chaining, we need to revise the time complexity a little bit. For insertion, we need to spend a constant time to find the hash bucket and constant time to append a new record. For search and deletion, however, we need to compare the search key with each record in the corresponding linked list. In this case, the time complexity is increased to OL, where L is the size of the linked list. As a result, our goal is to make L as small as possible to achieve more efficient time complexities. In other words, what we need to do is to avoid the cluttering of a lot of records in few buckets and distribute the records across the primary table as even as possible. Here, we'll present two simple recommendations to avoid record cluttering. First, we should use large key range, which should be much larger than the hash table size. Second, we should choose prime numbers to be the size of the primary table, as well as the divisor of the modulo operation in the hash function. Let's see why we need a large key range. Recall the example from the previous video. We converted a key string, or a name, to a real number by simply summing the ASCII code of its individual characters. We can see that the corresponding hash values are hundreds for the common names. If we are using a large primary table, which has 1,000,000 entries, it is easy to see that nearly all records will clutter in the first few hundreds of entries. In this case, the corresponding linked list of the former entries will be very long, while a large amount of memory space allocated to the hash table is wasted. To solve this problem, we can modify the way we convert key strings to real values. We apply a scaling factor to each character to inflate the resulting hash value using the formula given here. The scaling factor will serve as a base and be raised to its higher orders when applied to former characters of the string. For example, when computing the hash value for Alex, we will first multiply 37 to the power of 0 to the ASCII code of its last character x, 37 of the power of 1 to the ASCII code of E, 37 to the power of 2 to the ASCII code of L, and 37 to the power of 3 to the ASCII of A. We will then sum all inflated values to obtain the real value for the key, which is over 3 million here. Since the real value is larger than the primary table size, its corresponding hash value after the modulo operation can be any number between 0 through 1 million minus 1. In other words, the record may locate at any position of the hash table, addressing the local cluttering problem. Now, let's discuss why we recommend using prime numbers as the primary table size and the divisor for the modulo operation in the hash function. Consider the case where we have a scaling factor of 3 and a primary table size of 6. Note that 6 is divisible by 3. We can see that all the keys listed right here will have a hash value of 0. This is because for each key, its red numbers add up to an even number. When multiplied with some non-zero exponent of 3, the resulting number is divisible by 6. If the last blue number is also divisible by 6, then the resulting real value for the key string will also be divisible by 6. In this case, keys satisfying these two conditions will all be cluttered in the 0th position of the hash table. To avoid such cluttering, we should choose the scaling factor C and the table size M carefully, such that none is divisible by the other one. In another word, they should be coprimes. If we choose M to be a prime, then C can be any number other than M to satisfy the coprime constraint. There are other reasons why we should choose prime table size, and we will discuss it later in this module. After implementing the above two recommendations, another way we can use to reduce L is to simply make the table larger. Assume that the hash table contains n records and the table size is m. Then, if we can distribute these n records evenly across the m buckets, each bucket should contain n over m records on average. Note that n over m corresponds exactly to the average linked list length, L, we used before. This quantity is also called the load factor of the hash table. If we wish to achieve the claimed constant time complexity for hash table search, insertion, and deletion, we should make L in O1. If the load factor is too large, the corresponding operations may have to go over long linked lists and become very slow. On the other hand, if the load factor is too small, we may waste too much space in the hash table. Usually, we set the load factor to between 1 over 8 and 1 over 2. Which gives a nice balance of the time and space efficiency. Since the hash table size n keeps changing as we keep inserting or deleting records, maintaining the load factor within a range requires us to dynamically adjust the hash table size m. In the next video, we will discuss more details regarding dynamic hash table. In summary, we have discussed the separate chaining technique to avoid hash collisions. We have demonstrated the overall idea, analyzed the time complexity of the corresponding operations, presented two recommendations to avoid record cluttering, and introduced the notion of load factor. In the next video, we'll discuss issues regarding dynamically changed hash tables. Thanks for watching and see you next time.